أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. Assalamu alaikum, dear students. Today is the second lecture of numerical analysis. I will continue from the last lecture where I discussed the Newton forward difference formula with some examples. So now let's consider the second case, which is the Newton backward difference formula. Again, this formula is using for replacing data by a polynomial. Replacing data by a polynomial and then doing some interpolation. Formula is again for n plus 1 number of data points. F of xi starting from 0 and reaching up to n. So there are n plus 1 number of data points. That is, the points are x0 f of x0, second point is x1 f of x1, and last point is xn f of xn. And also we assume that the data is equally spaced data. Means that the distance between two consecutive points is the same, and that is given by h, which also we call as the step size. The Newton backward difference formula, if you look at this one, 0 is missing in this formula. I should start from 0. The backward difference formula is given by equation number 3. Now, if you look at this formula, slight modification from that of the forward difference. If you recall, the forward difference, we were using f of x0. But remember, that was the initial point of the data. But now here I'm using f of xn, where xn is the final point of the data. That is one difference. Second difference is minus 1 raised to the power k. Again, that we discussed in the class, and it's clear now. This term in that formula is replaced by minus s. Nabla stand for the backward difference. Nabla raised to the power k f of xn means that the kth order backward difference of the function f of xn. S, in case of forward formula, this was linked with the initial point. But remember, in this case, this is linked with the final point. Means that the value of S is equal to xn plus S into h. Since we are starting from the end point, the value of x will be greater than x0 and smaller than xn. When I say s is equal to xn plus s into h, so s is equal to x minus xn divided by h. So x minus xn will be negative because xn is the largest point. This coefficient, the expansion of this coefficient is given by this formula. Again, you can see that there should be k number of terms in the numerator, starting from minus s minus 0 up to minus s minus k plus 1 divided by this k factorial. And if I take minus sign common from all the terms, so you can see that in numerator there are k number of terms. If I take minus sign from every one, this will be minus 1 raised to the power k, and this will become plus, this will become s plus 1, and so on. This will become s plus k minus 1 divided by k factorial. And when I use this value in equation number 3, then formula 3 will take the form f of xn when the value of k is equal to 1. So this coefficient will give us minus s divided by 1 factorial. Multiply by minus 1 raised to the power 1. So minus and minus will become plus. So you can see that s divided by 1 factorial s power 1 f of xn, which is the first backward difference of the function f of xn. And when k is equal to 2, so we have minus 1 raised to the power 2. This will be positive, and when k is equal to 2, so 2 minus 1 is equal to 1. So the final point is s plus 1. So in other words, I can say this is s into s plus 1 divided by 2 factorial. And the value of k is equal to 2, so nebula square f of xn. When k is equal to 3, then you have from this coefficient minus 1 raised to the power 3, which gives you minus sign, and minus 1 raised to the power 3 in this formula, which is minus, so minus and minus will become plus, which comes here, and s into the value of k is equal to 3, so 3 minus 1 is equal to 2, so s plus 2 is the last term in this expansion. So you can see this is a s into s plus 1 into s plus 2 divided by 3 factorial. The value of k is 3, so nebula cube f of xn. And if we continue it, the value of k is equal to n. So look at the formula now. Minus 1 raised to the power n. It's coming from there. Minus 1 raised to the power n. So if I multiply these two terms, this will be minus 1 raised to the power 2n. Since 2n is even, minus 1 raised to the power even number is a plus sign. So you can see plus sign here. And when I replace k by n over here, so I will have s plus n minus 1 divided by n factorial nebula raised to the power n f of xn. So 4 is the alternate form of the formula 3. This is a backward difference formula. Now let us consider an example. So let's assume a function f of x is given to us, which is equal to cos of x plus log of x. Now remember, you can replace this function by a polynomial using the Newton backward formula, or you can do the interpolation. So I am doing the interpolation. I am taking the values of xi's to 2.1, 2.2, 2.3, 2.4, and 2.5. So you can see that the data is equally spaced. The distance between two consecutive points is 0.1. What is the target? Target is to find out the approximated value of the function at x is equal to 2.45. Using the backward formula, I said different polynomials, so means that I have to find out, use the polynomial of degree 1, 2, 3, 4, and 5. Why I'm reaching up to 5? Because there are 6 data points. So highest degree polynomial will be polynomial of degree 5. Now let us identify the intervals. You saw in the formula, I told you that s is equal to xn plus s into h. Xn plus s into h. So in this case, your xn is x5, which is equal to 2.2 here. Step size h is equal to, look at this one, 2.1 minus 2. 2.2 minus 2.1. So the step size is 0.1. Now let's find out the value of s. Let's find out the value of s. So if I solve this equation, I identify the values. This is the value of x, 2.45, x0, x1, x2, x3, x4, x5. The value of x5 is 2.5, which you can see over here. Step size is 0.1. So let's find out the value of s. X minus x5, 2.45 minus 2.5 divided by h gives you minus 0.5. Remember, in backward difference formula, the value of s is always negative. So you can see that this is the negative value. To go further, let's construct the differences table. So these are xi's to 2.1, 2, 3, 4, 5. This is x0, x1, x2, x3, x4, and x5. And you can see that the distance between two consecutive points is 0.1, which is the same. Now let's find out values of the function at these data points. f of 2 is given by 0.27700034441. Value at 2.1 of the function, value at 2.2 of the function, value at 2.3 of the function, value at 2.4 of the function, and value at 2.5 of the function, which is 0.11514711164. The target is to construct the differences table. So let's construct the differences table. The first difference is this value minus this value gives you this value. Remember, in case of forward differences, I was saying that this is a delta f of x naught. But in this case, in case of backward, I am saying this is nebula f of x1. This value minus that value. In backward difference, we are going in backward direction. Similarly, f of x2 minus f of x1 is equal to delta f of x1. Yeah, this is equal to nebula f of x2. Similarly, this value minus this value, which is a f of x3 minus f of x2, is equal to delta f of x2. Yeah, this is equal to nebula f of x3. Similarly, this value, which is f of x4 minus f of x3, is equal to delta f of x3. Yeah, this is a nebula f of x4. F of x5 minus f of x4 is equal to delta f of x4. Yeah, this value is equal to nebula f of x5. Remember, I will be using the backward. So in case of backward, this is a nebula f of x5, nebula f of x4, nebula f of x3, nebula f of x2, and a nebula f of x1. Now let's go to the second differences. Second difference is this value minus this value is equal to nebula of f of x2. Yeah, delta f of x naught. And if you come to this value, now this value minus this value gives us this value. This value minus this one will give you this value. This value minus this one will give you this value. Now, if I go to the use of the formula, this value is nebula square f of x5. This value is a nebula square f of x4. This value is a nebula square f of x3. And this value is a nebula square f of x2. Now let's come to the next difference, the third difference. This value minus this value gives me this difference. So I'm using the forward. So this value is equal to delta cube f of x naught. This value, this minus this will give you this value. And similarly, this value minus this value give us the value given by 0.00008651125. Now again, this value is a nebula cube f of x5. This value is a nebula cube f of x4, and this value is a nebula cube f of x3. Remember, I am discussing this in terms of the backward differences. Now let's go to the fourth difference. This value minus this value is given by this value. This minus this is given by minus 0.0000880939. And now if you look at this value, this is a delta raised to the power 4 f of x5. This is a delta raised to the power 4 f of x4. And finally, this value minus this value is given by the fifth difference. And this difference, this value is equal to nebula raised to the power 5 f of x5. Now, if you remember, in forward case, I use the first row. Now, in backward case, I'm using the last row, which I underlined. This was the construction of the difference table. Now, let's come to the different polynomials. Polynomial of degree 1. This is the formula, which I copied from there. Already you know that. Polynomial of degree 1 means that the value of n is equal to 1. The value of n is equal to 1. K starting from 1 up to n, so it will be starting from 1 up to n. F of xn, the value of n is equal to 5. The xn is equal to 5 in your data. But since I'm going for the summation 1, so this is remember, this is different from, this is the polynomial and this is the last point. So slightly this will be, this depends upon the degree of the polynomial. This is linked with that one, but this will be fixed already. F of xn, so f of xn was f of x5. That's the end point of the interval, as I told you before. When I say n is equal to 1, minus 1 raised to the power 1 is minus 1. Minus s divided by 1 factorial. Minus and minus will become plus. So that's the reason you can see s. F of xn, f of x5, and nebula f of x5 multiplied by s. You know that the value of s in this case was minus 0.5. Minus 0.5, if I substitute that value, this is the approximated value of the function using polynomial of degree 1 at the point x is equal to 2.45. But if you are looking, remember in this formula, this xn is x5. I should write the f of x5 for this particular problem. Now, if your target is to find out the polynomial, then the value of s is x minus x5 divided by h. x5 is known, 2.5, h is known, which is 0.1. So x minus 2.5 divided by 0.1. And if you replace the value over here and simplify s, this will give you a polynomial of degree 1, and this will replace by x. But remember, I am doing the interpolation, I am computing, that's the reason I replaced x by 2.45. So now let's go to the next polynomial. Polynomial of degree 2. Polynomial of degree 2. This plus another term when I replace n by, remember in this summation when I replace n by 2. So I will have minus 1 raised to the power 2, which is plus. Minus s into minus is minus 1. If I take the minus sign common, so I will get s into s plus 1, and that minus minus and minus will become plus divided by 2 factorial. This value is a nebula square f of x 5. And when you again replace the value of s, so you are getting the approximated value of the function using polynomial of degree 2 at x is equal to 2.45. Similarly, go for polynomial of degree 3. When I say polynomial of degree 3, so in this summation, this n will replace by k will start from 1 and will go up to 3. So up to 2 I covered in polynomial of degree 2 equal to 3. Minus 1 raised to the power 3 is minus 1, minus s, minus s minus 1, minus s minus 2. And if you take the sign common, minus 1 raised to the power 3 from there, minus 1 raised to the power 3 from there, so minus 1 raised to the power 6, and that is positive, and the value is given by this expression. Replace s by its value, and that's the corresponding value of your function using polynomial of degree 3 when x is 2.45. Go to the polynomial of degree 4. Polynomial of degree 4, this value is coming from the polynomial of degree 3 plus another term when the value of n, okay, start from 1 and reach up to 4. So there are 4 terms, and we have taken a minus sign common from all the 4 terms. That will become positive. Minus 1 raised to the power of 4 is positive, so that's the reason overall sign of this term is positive. And this is a nebula raised to the power 4 f of x5. And when you replace the value of s, so this is the approximated value of the function. Polynomial of degree 5. This value is coming from the polynomial of degree 4 plus the next term when in summation, when I say k start from 1 up to 5. So minus s5. There will be 5 terms, and if you take minus sign common from all these, overall the sign is minus, but in the formula there was minus 1 raised to the power 5. That sign is also negative, so minus and minus will become positive. That's the reason sign of this term is positive, and this value is a nebula raised to the power 5 f of x5. And when you replace the value of s in this formula, this is the approximated value of your function using the backward polynomial of degree 5 at x is equal to 2.45. Again, I will say that when we are increasing the degree of the polynomial, accuracy is increasing. So you can see that in different polynomials, you are getting different answers, but that's because of the polynomials. In this case, we are expecting that our error will be small as compared to the rest of the polynomials. This is the end of one example. Let me go to the another example. Now I consider the equation f of x is equal to sine x plus e raised to the power minus x. The data points are, if you look at the data points in this case, the distance between two consecutive points is 0.2. So 1.2 minus 1, 1.4 minus 1.2 is equal to 0.2. That is the step size. Data is equally spaced data, but the step size is 0.2. Now remember, I will be using the last point x naught is 1 and xn, which is x5, that is given by 2. What is the target? Target is to use the backward difference formula as we discussed before to find out approximated value of the function at 1.95. So you can see 1.95 is close to the endpoint, and we have to use the different polynomials. So I mean that polynomial of degree 1, 2, 3, 4, and 5, since total number of points are 6. Now let's identify the unknowns in the formula. The value of x. This is the value of x. The value of x5 is 2. So x is equal to xn plus s into h. Again, backward formula, s will be negative, and the value of x is 1.95, the value of x5 is equal to 2, step size is 0.2, and when I compute s from here, that will give me x minus x5 divided by h, which is minus 0.25, and you can see that the value of s is negative as we were expecting. Construct the differences table. These are the data points: 1, x0, x1, x2, x3, x4, and x5. You can see the distance between the consecutive point is 0.2. The step size is 0.2. Let's compute the values of the function at xi's. So the value at 1 is given by this relation of by this value 1.20935046. The value at 1.2 is given by this value at 1.4, value at 1.6, value at 1.8, and value at 2. Again, keep your calculator in radian mode if you are using the calculator. Find out the differences table. So let's find out the first differences. This value minus this value is given by this value. This value minus this value is given by this one. This value minus this is given by this value. This value minus this value minus this is given by this value. Now this value minus this value is given by this expression. This is the first differences table. In forward differences, I was starting from here, but in backward differences, I have to start from the endpoint. So remember, this is a nebula f of x5, nebula f of x4, nebula f of x3, nebula f of x2, and nebula f of x1. Go to the second differences. This value minus this value is given by this value. This value minus this is given by. This value minus this value is given by. And this value minus this value is given by this one. So the construction is the same as you did in previous examples, but I'm using this in a different way. This is the second difference. So remember, this is a nebula square f of x5, nebula square f of x4, nebula square f of x3, nebula square f of x2. You have to start from the endpoint and move in backward direction. Now let's go for the third differences. This value minus this value is given by, this is the minus 0.00432049. This value minus this value is given by this value. Now this value minus this value is given by minus 0.00043178. Now let's look at this column. This value is a nebula raised to the power 3 f of x5, nebula raised to the power 3 f of x4, and nebula raised to the power 3 f of x3, which we recognize in this way. Fourth difference, this value minus this value is given by 0.00196343. This value minus this value is given by this value. Now remember, minus 0.0019138882, this is a nebula raised to the power 4 f of x5, nebula raised to the power 4 f of x4. And finally, this value minus this value gives us the fifth difference, and which is given by minus 0.4049551. And this value is a nebula raised to the power 5 f of x5. So we constructed the differences table. No changes from the previous examples, the procedure is the same, but we are using the last row and backward formula, the values which I underlined, that I will be using n. And your formula, this is nebula f of xn, which is, f of xn, f of x5, nebula f of xn, nebula square f of xn, nebula cube f of xn, nebula raised to the power 4 f of xn, and nebula raised to the power 5 f of xn. These are the values which we will be using in the in our interpolation. So now let's go to the this is the formula. Polynomial of degree 1. Polynomial of degree 1, so it means, remember this xn, this is x5 for this particular problem. F of x5, this is f of x5, which is clear from your table, plus n is equal to 1, k starting from 1 up to 1, minus 1 raised to the power 1 is minus 1, minus s1 is minus s, so minus and minus will become plus. That's the reason you can see the positive sign for this value, and this value is a nebula raised to the power 1 f of x, and this is the coming from the first backward difference. And when you substitute the value of s, which was minus 0.5, the approximated value of the function at x is equal to 1.95 is given by 1.0682616162. If you are looking for the polynomial, so replace the value of s. The value of s is equal to x minus 2 divided by 0.2. So that will be in terms of x. I told you that you can replace your data by the polynomial also. So that will be giving you the polynomial. And when you are doing the interpolation, so this is the interpolated value of the function. Polynomial of degree 2. Polynomial of degree 2. In this summation, k starting from 1 up to 2. K is equal to 1. I discussed it over there. When k is equal to 2, so this is the value. Minus 1 raised to the power 2 will give you plus 1. Minus s2 will give you minus s into minus s minus 1. If I take minus sign common, that will become plus divided by 2 factorial. This value from the table is a nebula square f of x of 5. And when you replace the value of s, you are getting this is the approximated value 1.071278994. Approximated value of the function 8x is equal to 1.95 using polynomial of degree 2. Polynomial of degree 3. The value of k will be starting from 1 up to 3 in this summation. Again, I'm telling you xn is the endpoint. So f of x5. F of x5, already you have used it over here. K is equal to 1. What's this relation? K is equal to 2. We got this value when k is equal to 3. So this is the value. K is equal to 3 minus 1 raised to the power 3 minus 1. Remember, this was the minus sign. K is equal to 3. There will be 3 terms. Minus s minus 1 minus s minus 2. And if you take the sign common from all the 3, you are getting minus sign. Minus and minus will become plus. And you can see that the sign is positive. This sign, this is the sign of a nebula raised to the power 3 f of x 5. So this is the value, and when you replace the value of s as we computed before, so that gives you the approximated value of the function at x is equal to 1.95 using polynomial of degree 3. You can see all the 3 values are different, but as we are increasing the degree of the polynomials, the values are going closer and closer to each other. Now let's go for polynomial of degree 4. In this summation, the value of k is starting from 1 and reaches up to 4. Again, f of x5, k is equal to 1, k is equal to 2, k is equal to 3 we discussed in polynomial 1, 2 and 3. When k is equal to 4, this is the value coming from using the polynomial of degree 3 plus when k is equal to 4 minus 1 raised to the power 4 positive minus is 4. 4 terms, negative sign from everyone, that is positive, and s minus 1 is minus s minus 1 minus s minus 2 minus s minus 3, and if you take minus sign common from r, so they become plus, divided by k factorial, which is 4 factorial. This value is nebula raised to the power 4 f of x5. And when you substitute the value of s in this formula, that is the approximated value of your function using polynomial of degree 4 at x is equal to 1.95. Come to the polynomial of degree 5. Polynomial of degree 5. Polynomial of degree 4, so I use the value, the k starting from 1 up to 5. K starting from 1 up to 4 are used in the polynomial of degree 4, which is clear from here. And polynomial of degree 4, this is the value coming from polynomial of degree 4, and plus this is the value corresponding to k is equal to 5. Minus 1 raised to the power 5, so remember negative sign, minus s minus 1 minus s minus 2 minus s minus 3 minus s minus 4, and if you take minus sign common, so 1 2 3 4 5, minus 1 raised to the power 5, minus sign from there, minus sign from this formula, so minus and minus is plus, so you can see the sign of this term is positive, and this is a nebula raised to the power 5 f of x5. And when you replace the value of s by minus 0.5, your approximated value is given by 1.0712326770. So remember, this is the approximated value of the function using polynomial of degree 5 at x is equal to 1.95. So you saw in this lecture that how we used the Newton backward polynomial to find out the approximated value of the function at x is equal to 1.95. Again, we are expecting that the greater the degree of the polynomial, error will be small. So we are expecting that this will be more accurate answer as compared to the other 4 polynomials. This is another example using the Newton backward difference formula. If I summarize it, we discussed the Newton backward difference formula. There are different formulas. You can do the interpolation. The people are trying different cases, so this is in other form using the differences table, and I told you that these techniques are using for replacing the data by the polynomial, and then you can see that to study the polynomial, find out the derivatives, integration, it's easy as compared to the other functions. So you can replace your data by the polynomial, and then you can study according to your choice that what you are looking for. And also you can do the interpolation. So I hope the points will be clear. And in case of any problem, you can contact me. Already you know about my contact, and inshallah I will try to solve the problem which you are facing, and hope all your good health, and safe return to the institution. Thank you very much.